So now I will describe the thermodynamic limit and what a thermodynamic limit means, and then I will go to the ferromagnetic to the paramagnetic transition and Ising model Hamiltonian. So what is the thermodynamic limit? So you might have heard about this word that when we are in thermodynamic limit, the concept of phase transition are defined and every other things. But what is it and how it is defined, that is quite poorly known among you. So the proper definition, or you can say the idea of thermodynamic limit, today I will be discussing. So since the P energy is extensive quantity for large n limit, that means what I mean is that the P energy F, so the P energy is extensive for large n, and so what that by the word extensive for large n, I want to mean that F varies proportional to volume, if it varies as volume, and if we expect a finite size effect, like when, so you cannot in the ideal simulation, or you can in the proper computer simulation, you cannot go up to infinite system, so there will be some finite size effect. So we expect for a finite size system the P energy to be varies as the following. So we expect for a finite size system, so the P energy will be written as V into F of B plus S into F of S plus some order of magnitude L to the power D minus 2 term. So this is for a d dimension system. So this is for a d dimensional system. This is for d-dimensional system. So what does it mean? So the P energy contribution will be depend on the bulk P energy plus the surface P energy, and this FB and FS. So FB is basically bulk free energy per volume. So bulk free energy per volume, and this Fs is basically surface free energy per volume, surface P energy per area, P energy per area. And so as the volume tends to infinity, so this Fp equal to limit V tends to infinity F by V. So the quantity when Fb is basically the Fv tends to infinity limit of the ratio F by V, and similarly you can define the Fs using the total form of the free energy. So when area goes to infinity, and F minus V Fb by A is basically the ratio is called Fs. And now for a lattice system, so this becomes, so for a lattice system, so Fb is equal to, so there are basically there are n number of lattice points, or maybe n number of atoms in the lattice. So that means the number will be n tends to infinity F by n. So that for a lattice system, Fb basically defines like this. And now so these limits are basically called the thermodynamic limits. So these are thermodynamic limits. So these are called thermodynamic limits. Thermodynamic limits. Now why do we want to need these thermodynamic limits? Because the concept of phase and phase transition are defined in the thermodynamic limit. So we shall see that for a system to exist in the thermodynamic limit, the underlying forces of the interaction should be short range. So like the short range I want to mean that, so like the interaction energy, if it is long range interaction, then basically your thermodynamic limit will be not valid. So it diverges in the thermodynamic limit. Like let's say for a system of n charges packed at a uniform density, so they are, let's say, interacting via Coulomb force, then you can calculate this E, which is the free energy, which will vary as the RQ into RS square because of the Coulomb force, and you can see this is varies as R to the power 5, and if you take the ratio F by V, which is here I denoted by E, so if you take the ratio E by V, then it will varies as R square, and as R tends to infinity, this ratio tends to infinity, which diverges the thermodynamic limit. So this is basically the thing for the long range term. So this is the long range interaction term. So that's basically the point. So we shall see that for a system that exists in thermodynamic limit, the underlying forces of interaction should be short range. So that is the point here. That's why we want to study that's why we have studied this thermodynamic limits. So now by this point the idea of thermodynamic limit is clear to you. So now I will straightly go to the ferromagnetic and paramagnetic state, and which is the main focus of our study. So now you can see here in this picture that this is a basically magnetic domain. This is basically a FESI sample, which is basically which is known to be a magnetic ferromagnetic material. And as you can see here, there are several domains of like you can see like this is one domain, this is one domain, and here also there are some domains, right? So this is basically the domains of spin. So as you can see here, there are several domains in the material. So they are basically the magnetic domains which is found in the ferromagnetic material. Now let me define the ferromagnetic material. What is a ferromagnetic material? So in ferromagnetic material such as iron, so let me write it here, new page after, yeah. So ferromagnetic material like iron. So here basically the point is that these materials form magnetic domains. So they form magnetic domains. And the word magnetic domain, I want to mean that, so in a magnetic domain, all of the spin in a certain region of the material are aligned, and these materials have large number of domains that are oriented in a different directions. So as you can see here, there are large number of domains. I have only pointed out some of them I have just pointed out. So so they have large number of domains oriented in different aligned in different direction. So on an average, the magnetic moments of each of these domains cancel out, and the net magnetization of the material is 0. So although some of the domains have although in a ferromagnetic material there are several domains, and the spins are aligned in several direction, but the net magnetization is 0, because on an average the the magnetization is 0. That's why, so the magnetic moments of the domains cancel out, and they got this net magnetization will be equal to 0. But at low enough temperature, magnetic domains can align by an external magnetic field. So at low enough temperature T, magnetic domains can be aligned can be aligned by an external magnetic field. So the external magnetic field exerts a torque on the dipole. So as you know that, so let's say I rename it as B. So now B, so this B applies a torque on each dipole, right? But since the magnetic dipoles tends to align with their neighbors, so they resist. So since the magnetic dipoles tend to align with their neighbors, so they resist. Neighbors, so they resist. So what does it mean? So let's say if you have a ferromagnetic material and at low enough temperature, so there are several magnetic domains as you can see in that picture, and if you apply a magnetic field, so then that magnetic field will apply a torque on each dipole, because you know that each electron has dipole moment. So each electron has dipole moment equal to, so some mu equal to some gamma into capital S, where gamma is the gyromagnetic ratio. So this is the gyromagnetic ratio. So this you might have heard, and S is the spin angular momentum of the electron. So S is the spin angular momentum of the electron. So this is basically the thing you know. So you know that each electron has some dipole moment, and so as they have some dipole moment, when you apply a external magnetic field, so what will happen? This magnetic field will apply a torque on each dipole, but since the dipole tend to align with their neighbors, so they will resist against the magnetic field, right? So that is the thing. And at domain boundaries, the neighboring spin are lined up in different direction. So when you see the domain boundaries, so let me draw a picture. So let's say this is your magnet. Let's say, let me draw it with some domains. Okay, so let's say this is one domain, this is one domain, this is another domain, like that, and like so on. And let's say this is your one domain, and this arrow I used to draw some spin. So this is basically your one domain, and this is your another domain. Let's say this is some other domain with aligned in this direction. So as you can see, on an average, the total net magnetization will be equal to 0, but the individual domain has their own magnetic moment. And as you can see, at the domain boundaries here, this is called domain boundary because here two different type of domains will match. So the domain means basically this is a domain of this is a domain of up spin, this is a domain of down spin, like that, and this is called the domain boundary. And so at domain boundaries there are neighbors. So at domain boundaries there are neighboring spin that are lined up in different direction, as you can see. So here the spin is in up direction, here is the spin is in down direction, and the torque will start to reorient that spin. So the torque, due to the magnetic field, the torque will try to reorient this thing, and that are not aligned with the magnetic field. So if it is not aligned with the magnetic field, the magnet torque due to the magnetic field will try to align them in the same direction as the magnetic field. And so then basically what will happen is that so the domains parallel domain, the magnetic field, the domain of the spin will try to become parallel to the direction of the magnetic field. And if you apply strong enough magnetic field, the dipoles in the entire chunk of the material will be in the direction of the magnetic field. So that will be orientated in the direction of the field. So in ferromagnetic material, this process is not reversible. So once you so in ferromagnetic material the if you apply a magnetic field, so if we apply a magnetic field, so then what will happen is that so the material has material has some non-zero magnetization even if you remove the field. So the material has a non-zero magnetization even if you remove the magnet. So that means is the following. So let's say if we have a ferromagnetic material which I denote by F. So let's say ferro. So if you have ferromagnetic material, ferromagnet, so then if you apply some field, so now it has the magnetization equal to 0 right now, and if you apply some field, so then after that it will be like it will be aligned in the direction of the field. So if you apply the field in this direction, and this will also be rotated in this direction, and then if you remove B, then the material has some M which is non-zero. So it will never be go to 0 once you remove the magnetic field. So for a ferromagnetic substance there exists a temperature which is known as the Curie temperature, and at low and up below which the material become ferromagnetic, and up above which it will become paramagnetic. That means is the following. So the definition of the Curie temperature is that so it is a temperature above which if your temperature of the material is greater than Tc, then the material is no longer ferromagnetic. So at low temperature the interaction between the spins cause them to align. So but above the Curie temperature what will happen is that the material undergoes a phase transition and it becomes a paramagnetic substance. So that is the model which I am going to study. So here basically the point is that the above the Curie temperature the material will no longer be ferromagnetic, and the material will undergo a phase transition and it will go from ferromagnetic to the paramagnetic state, which is called second order phase transition. So it will become ferro to para, and this is called second order phase transition. So this is basically the thing which we are going to study in this short lecture. And so when you increase your temperature of the system greater than equal to Curie temperature, what will happen is that the magnetic moments will orient randomly, and that is because of the thermal effects, and that randomness will kill the interaction between the spin, and they will become all random, which will make the material paramagnetic with magnetization equal to 0. So that is the thing which we are going to study in this lecture. And going from paramagnetic to ferromagnetic to paramagnetic, the magnetization will go from 1 to 0, and that transition is a continuous transition, and that is also known in the from the theory of the phase transition that I have described earlier. And so that is basically the thing which we are going to study today. And Ising model is one of the model and simplest model which will show this ferromagnetic to paramagnetic transition, and that's why it is the matter of study and important study in all over the fields. So now what I will do next is basically to show some illustration and how the ferromagnetic or paramagnetic material will look like, and then what I will do is I will just derive the Ising model Hamiltonian from where it comes, and so that is the thing that I am going to do next. So let me draw a ferromagnet for you first. So let me introduce a new page. So how a ferromagnetic material will look like? So the ferromagnetic material will look like the following. So you have spin aligned in a particular direction. So this is basically parallel. So sorry for my drawing, but these spins are strictly parallel with each other, and this is called a ferromagnetic material. So this is ferromagnetic. And now, so if you have spins like these, so like they are like these, and these, and these. So these are basically random orientation of the spin, and this is called paramagnet. However, so as you can see here I am drawing the spins with some angle and so on, but in the usual Ising system, so in usual Ising system, so this spin are strictly 90 degree, and the paramagnetic state will mean something like this. So this will be like random up and down spin, and which will make the total magnetization equal to 0, and that is basically the paramagnet in Ising model. So you cannot have spin which have some alignment like this. So in usual Ising model you don't have, but there are several other models like Heisenberg model, XY model that I will describe briefly, and you can see there the spins can align like this. But in usual Ising model the spin cannot be like this, so they will be like this, and this will give some zero magnetization in the paramagnetic state. Now there is another thing which is called the anti-ferromagnet, Ising anti-ferromagnet, where you have spins like the following. So you have alternative up and down spin, alternative up and down, so like this. So now, so this is basically called anti-ferromagnet. Now there is we do have a transition from anti-ferromagnetic state to paramagnetic state, and that is, and here there is a temperature which is called nil temperature, and above which the material become paramagnet. So that is the thing. So here the point is that point is the following. So in anti-ferromagnet the spins are alternative up and down in space, and the net magnetization is 0, because you know that this is, if all the spins are alternatively up and down, the net magnetization will obviously be equal to 0, and so then the order parameter cannot be the magnetization, and for the usual ferromagnetic to paramagnetic transition we can take the magnetization as our order parameter, but in the anti-ferromagnet to paramagnetic transition we cannot take paramagnet to anti-ferromagnetic transition we cannot take the order parameter as the magnetization, and what we will do is that we will take another quantity as our order parameter. So I might have already told you that the finding an order parameter is very difficult in any system. So here the order parameter is basically called the staggered magnetization, which is basically you will took in the case of staggered magnetization we will just look at every other spin, say is not 0. So that is what we will look. So we will look at the only up spin or down spin like that. So that will be our order parameter in this case. And here like ferromagnet, here second order phase transition from a paramagnet to anti-ferromagnet occur, and if you could put on a staggered magnetic field that altered direction in side to side, we could also measure a staggered susceptibility also, and that will also diverge at Tc. So that is basically the thing. And now, so now I will describe the Ising Hamiltonian and from where it originates. So that is my next topic of study, and then I will do the other things. Okay, so before going to that, so let me draw some other picture as well. So so in the ferromagnetic material, so as I already drawn earlier, but let me draw it again. So in a ferromagnetic material, you have several domains like these, and in the domain there are spins like in the domains there are spins like they are aligned in a particular direction in every domain, but the net magnetization is 0, and like these, and so on. Now this is basically if you apply a magnetic field H and in the up direction, so what will happen, these domains will try to align with this magnetic field, and in the final configuration when we apply a strong magnetic field, all the spin will become in the direction of the magnetic field. So that is basically the point of applying a magnetic field. So alignment of domains, so when a ferromagnetic material is exposed to an external magnetic field, so you can see in this picture is that these domains are unaligned, and as the magnetic field applied, you can see the domains are aligned with direction of the magnetic field. So that is basically the thing. And now, so what I will describe next is basically the Ising Hamiltonian. And so let me tell you about the history of the Ising model little bit. So then I will just go to that thing. So in this the spin model, which is the Ising spin model, so it is one of the most interesting topics to study, and because it is the simplest model which shows this ferromagnetic to paramagnetic transition, which is the second order phase transition, and this spin model is first proposed by Wilhelm Lenz, and it is in 1923. So he proposed this problem to his graduate student called Ernst Ising, and so Ising showed that there is no phase transition in 1D, and in which he showed it in 1925, and then going from he found that there is no phase transition going from t is equal to 0 to infinity in one dimensional system. So he was very upset that like he was expecting some phase transition, and from this argument from this argument like the no phase transition in the 1D, so he also argued that there will be no phase transition in the two dimensional and higher dimensional as well, but that is actually wrong. And then comes the Onsager story, and so then Onsager basically solved the 2D problem, 2D Ising model in 1944. So he actually didn't publish the work. So in a conference while he was describing about the phase transition, it was revealed that time. And so the Ising model, the first term Ising model that is used by R. Perils, and that is in 1936. So that is basically the all history of the Ising model. And in 1944, Onsager showed that Lars Onsager shows that the 2D Ising model do have a phase transition, and that is basically violating the statement of Ising, where Ising made the statement that there will be no phase transition in higher dimensional as well. But Onsager showed that we do have a phase transition in 2D Ising model, and so in that is also similar to that is seen in a real ferromagnet. He also showed that mean field theory. So there will be some arguments about the mean field theory that I will describe in the last part of this short course. So ferromagnets are basically the magnetic. So they are basically the magnets that can be found in our refrigerator doors holding up nodes. So that is basically the refrigerator magnet type of thing. So this is all the story about the history about the Ising model, and so that is basically the core of the study. And now what I will do, I will describe the Hamiltonian. So our first case to find the reason of the magnetism is basically you can see that the dipole-dipole interaction. So electrons have some. So electrons have a magnetic moment which is some m equal to minus 2 mu v some s vector, and so that is associated with the intrinsic spin angular momentum of the electron. So our first case would be that the magnetism was due to the dipolar interaction of the magnetic moments. That dipoles have an associated magnetic field, so we might have expect that the each moment to align in the magnetic field of its neighbors. So let me calculate the interaction energy of the dipole. So let's say if you have a two dipole, so electron has some dipole moment. So if you have two dipole like m1 vector and m2 vector, and the dipolar interaction so let's say if you have a two dipole magnetic dipole separated at a distance r, then basically the energy for that will be equal to mu 0 by 4 pi r q, and under bracket m1 dot m2 minus 3 m1 dot r cap into m2 vector dot r cap. So now this formula you are very familiar. I think in electrodynamics you might have studied this formula, that two interaction between the two magnetic dipole and how it looks. So this is how it looks. So the reason why we are studying this point is that we are trying to find the source of magnetism in this magnetic material, in any magnetic material. So for our first case is basically the magnetism in the magnetic material is due to the electrons intrinsic spin angular momentum, and that gives rise to a magnetic moment. And if you have some magnetic moment, then if you have two magnets separated by a distance r, then basically they will be interacting via this potential, via this interaction energy, which is dipole-dipole interaction energy. But if you calculate the order of magnitude of the energy, what will you find is that this U will be of the order of 10 to the power minus 23 joule. If you substitute any value, typical value of the magnet, so let's say if your magnets are separated by 1 angstrom, and then if you substitute the value of the magnetic moments and everything other thing, you will get a number which is 10 to the power of the order of 10 to the power minus 23 joule. And now the spin should be disordered, like, and if the thermal energy is of the order of, so let's say if the thermal energy is of the order of kBt, so it is this thermal energy is comparable with the to be comparable with the thermal energy with the interaction energy, so it required to reverse the spin. So this should suggest that the temperature is around 1 Kelvin, right? So if you so this spin should be disordered, and if the thermal energy kBt is comparable with the energy U required to reverse the spin, this should suggest that the temperature will be around 1 Kelvin, and which is in the cases of iron and cobalt is too small, because in the cases of iron and cobalt the transition temperature is of the order of like 1000 or something, so 3 orders of magnitude higher. So that's why this cannot be the reason of the magnetism. So there is something else, and what is that else is basically the exchange interaction. So the exchange interaction is the following. So let me write it down and introduce a page. Okay, so the point is basically the exchange interaction. So now so the exchange interaction, what will happen is that this will basically the quantum mechanical thing, and in that the mechanism for the spin alignment in magnets comes about indirectly as a result of the electrostatic interaction and anti-symmetric property of the electron wave function. So antisymmetric property is, by the word antisymmetric property I want to mean that this phi of r is minus of phi of r, phi of minus r, sorry. So okay, sorry, I think I have written right, yeah. So if you reverse this thing, so it will be like, so if you more sophisticatedly if you write this, so this will look something like this. So this is r1 sigma 1 including the spatial part and the spin part, and r2 sigma 2 and so on. So this will be equal to minus of phi r2 sigma 2 r1 sigma 1 and so on. So this is basically the anti-symmetric property of the wave function of electron, and which is fundamental property of all fermion wave function. This is the anti-symmetricity is fundamental property of a fermion, and electron is a fermion. And this is in general rule that the leads to the Pauli exclusion principle, and you already might have known that this no two same spin electron can be stayed in a same orbital, and that is basically due to the anti-symmetric property of the fermions, which is electron. And now, so for two electrons, let's say, which are known to be in the states alpha and beta, so the anti-symmetric contribution will be like this. So let's say for the two electron wave function, phi 1 2 will be equal to alpha 1 beta 2 and minus alpha 2 beta 1. And now, so what the symbol 1 2 are basically the shorthand rotation for the r1 sigma 1. So this r1 sigma 1 I just write 1, and r2 sigma 2 I just write 2, and r1 is basically the spatial part of the wave function. The wave function has two parts, one is the spatial part and one is the spin part. And now, so here so now if the two state alpha and beta are the same, then phi 1 2 will surely be vanish, as you can see in this equation. And now so the two electrons cannot occupy the same state because the wave function cannot vanish, and that is the thing that's which introduce the Pauli exclusion principle. And to the extent the spin orbit coupling can be neglected, and the interaction between the two electron in simply is basically the Coulomb interaction, which is the E square by 4 pi epsilon 0 r12, and it can be included in the Hamiltonian. Let's say you can define the Hamiltonian, right, H of 1 comma 2, and along with the kinetic and single particle potential energy. So along with the kinetic and potential energy, we can also include the electrostatic energy, which is E square by 4 pi epsilon 0 r square, E square by 4 pi epsilon 0 r, which is the potential energy. And now, because the energy is symmetrical and does not depend on the spin variables, so the solution of the Schrodinger equation will be the following. So which is H operating on psi r1 comma r2 equal to E psi r1 comma r2, and these are basically the vector quantity. So now, so this basically determines the energy levels of the two electrons, and they are themselves either symmetric or anti-symmetric. And this basically thing is the following, is that so the psi 1 2 is plus minus psi 2 1, and this can be either symmetric or anti-symmetric. And this is very easy to see that for non-degenerate level like psi 1 2 and psi 2 1, each solve the same Schrodinger equation. So it also will solve the Schrodinger equation, this also will solve the Schrodinger equation. And if the label is non-degenerate, the energy level, if the energy level is non-degenerate, then the two function must be identical apart from a factor of so like if they are non-degenerate, and the two function must be identical apart from a factor because of this relation. So this psi 2 1 we can write it as C equal to psi 1 2. So this still I don't know what is C, and then basically when you substitute in this equation, so what you will find as that C square is equal to 1, and this will give rise to C equal to plus minus 1, which I have written here. So that is the thing. So so the consistent so this is the consistent of the Pauli exclusion principle as well, and the complete wave function will be phi 1 comma 2 will be equal to the psi r1 comma r2, which is spatial part, and the chi sigma 1 comma sigma 2, which is the spin part. So that is basically the product of space dependent and spin dependent function. And so if this psi is symmetric, then this chi will be anti-symmetric and vice versa. So it will also go as the vice versa thing. So now let's say see the interaction energy term, and let's say if you have a energy state, if you have the electrons in a spatial states A and B and assume to be degenerate energy, so then there can be one anti-symmetric wave function, which is let's say chi equal to, so let's rename it as chi s, and which is equal to this up, and or you can say in terms of 1 2, but let's say light is that, so 1 and 2, and then down 1 and up 2 by root of 2. So this is the only one anti-symmetric wave function, and this is basically a singlet. So this is singlet state with Sz equal to 0. So singlet state means Sz will be equal to 0, because you can see this anti-symmetric property, and so this will also correspond to S mod capital S equal to 0, and corresponding symmetric wave function will be the following. So psi S will be equal to A1 B2 plus B1 A2 by square root of 2, and on the other hand, the triplet state will be like the following. So triplet state will be can be like up 1 up 2, means both the up state of 1 and 2. Then also you can have something like up 1 down 2 plus down up or like the opposite, which is the down 1 up 2 divided by square root of 2, and also the both are down. That is, these are also all the three possibilities for the symmetric case. And now, so this case, in this case, Sz will be equal to it can be 1 when all are up, and then it can be 0 when up down is there. It can be -1 when all are down, and capital S will be equal to 1 here. So this is basically the triplet. And now, so the point is that here, and if you calculate the so now if you, let's say, suppose the singlet energy state is greater than the triplet energy state, so then so then basically if you write the energy of the as a function of spin, so E effective of S, then it will be like Es minus half of Es minus Et, and then basically the S into S plus 1, right? So why we are writing this? Because we can do the following in this case, because you can write it as it will be equal to Es when S equal to 0, and it will be equal to Et when S equal to 1. So this is a nice way of writing this effective energy. So whenever S is equal to 0, it becomes the singlet state. If you substitute S equal to 0 here, you will get Es, and whenever S is equal to 1, you will get Et, because of this formula. This is a particular form of writing this same thing in a different way. So that is basically, this correspond to the singlet energy when S is equal to 0. It corresponds to the triplet energy when S is equal to 1. So let me introduce a page after. Yeah. So then basically, if you are agree with this formula, then your H effective is basically equal to Es minus half of Es minus Et, then S, this is basically the eigenvalue of S square. S into S plus 1 is equal to, so this we know that, so the eigenvalue of S square Lm is basically, sorry, not Lm, so S square eigenvalue, so this is eigenvalue will be equal to S into S plus 1 h cut square. So S into S plus 1 will be equal to S square by h cut square, and then what you can do is basically you can write S square equal to basically S1 plus S2 whole square, and this will be equal to S1 square plus S2 square plus 2 into S1 dot S2, and so this is basically half h cut square. So this is basically h cut square, because for one of them it will be like, so not h cut square, so this is basically 3 by 4 h cut square, and this is also equal to 3 by 4 h cut square, because if you substitute in this eigenvalue formula, you will get that the eigenvalue of S1 square will be equal to 3 by 4 h cut square, and eigenvalue of S2 square will be equal to 3 by 4 h cut square, and then 2 S1 dot S2, and then what we will get, you will get 3 by 2 h cut square plus 2 S1 dot S2, right? So S square value you get till now. So now if you substitute it in the formula, so what will happen is that, so H will be equal to a function of S1 S2 and H effective. So then this will be equal to this Es Es minus half of so this will become now, so this is Es minus Et, then S square will be like this, so this will be 3 by 2 h cut square plus 2 s1 dot s2, right? And so this is the thing, and then what you will get is basically you will get some constant times minus of j s1 dot h2. So j is also some constant, and so now it's basically here it comes the Hamiltonian of the Ising model. So we basically neglect this constant term because it's just a constant, you can take it 0, and this is basically the Ising model Hamiltonian that we used to write, and this is how it comes from the quantum mechanical approach. So this is the way you will get the Ising model Hamiltonian, and so you can now generalize it to 1 dimension, 2 dimension, 3 dimension, and so on. So this is how it comes. So so this is the thing that I was trying to describe you, and so this is basically very important to study, because either until you know this thing, so it will not be clear to you, and why it is coming, and why this Hamiltonian, and how this Hamiltonian came. So it has basically a microscopic quantum mechanical origin, and that is what it is. So that is just I described. So this is the thing. In the next is I will be talking about the 1-dimensional and 2-dimensional Ising model Hamiltonian, and so let me talk about this. So in 1 dimension, what will happen is that this term will be look like so j into si plus 1, and the sum will be over all the nearest neighbor ij, and this will basically summing over all nearest neighbors. So this angular bracket means basically is the following, that it is the sum over the all the nearest neighbor spin. And now so there can be also a term which is equal to the magnetic field, and that will go from I equal to 1 to total number of spin n, and then will be si. So this will basically an external magnetic field term. If you want to apply, you can apply that, and that is also one can study with the Ising model with the external magnetic field, and this is the thing. And so here this is basically in 1 dimension 1D, and here this point will be like this. So let's say this is your I equal to 1, this is your I equal to 2, this is, so this, let me draw the spins. So this is your I equal to 1, this is your I equal to 2, this is your I equal to 3, and so on, like that. And if you consider this spin, and these two are basically the each neighbor. So then in 1D, if I spin neighbor of, so let me write it properly. So in 1D you have 2 neighbors. So in general, in D dimension, please note it down, in D dimension the number of neighbor is 2 into D. So this is the thing. So in 1D, you have 2 neighbors, which is I plus 1. So if you have this spin I, then the neighbors are I plus 1 and I minus 1, like this, and this will be neighbor of 2. So these two are the neighbors. So this spin has the neighbor this and this. So this is basically the thing. And here the H is basically the external magnetic field you want to apply with, and with this sum over Si, and the magnetization is defined as the sum over Si, I equal to 1 to n and Si divided by n. So this is the magnetization per spin, which is defined like this, and this acts as an order parameter. But in 1 dimension there is no phase transition, that I will describe in a while, and this is basically the 1D system, and this is called Ising chain. But now if you have periodic boundary condition, which is the following, So if your last spin, which is in plus 1, equal to I1, and if your I0 is basically equal to In, so this is basically the periodic boundary condition will be applied. And when you apply PBC, which is periodic boundary condition, and this will be like a circle, and you start with I equal to 1, then goes up to I equal to 2, so on, so on, so on, and then I equal to n, and after that In plus 1 equal to I1, and then so on. So this is basically under the periodic boundary condition. And one thing you notice that, so if you have periodic boundary condition, then all the spin has exactly equal to 2 neighbors, because you have the periodic boundary condition. But if you have free boundary condition like this, the n spin will have only one neighbor, because it can only see this part, not this part, and this spin can see only this part, not this part. And that's why for a free boundary condition, you have for free boundary condition n spin have one less neighbor, but for PVC, so that is one of the importance of using PVC. But for PVC, we have exactly same number of neighbors for each spin. So that is basically the difference. So if you have same number of spin for the same number, if you will have same number of neighbors for all the spin in periodic boundary condition. So this is basically the one dimensional picture, and it is also called the Ising spin. And then comes the 2D part, which is the following, which is the most popular one, which has the phase transition. So it is written as like this, so minus j and ij, this is the nearest neighbor sum, jij and si sj, then minus of, you can write in terms of minus also, plus also, whatever I equal to 1 to n h si. And you can actually make okay, sorry, this term will not be there. Okay, so and you can actually include that term, and so this j inside this thing, and that basically allows you to allows you to verify to classify j at each side ij. But here I am taking j as a constant, that's why I am writing it outside the summation, and that is also you can take here, and you can write ji of j, and that is the thing. And this is basically the 2D Ising model, and here you have the representation like these following. So you have this grid like structure, you can take square grid, you can take hexagonal grid, or so on, and you have this thing. So sorry for my bad drawing, but still understandable, I guess. So yeah, here and then this thing. So let's say if you have a spin like here, so let's say this is I comma j, then your neighbors are the following. So this is I plus 1 comma j, this is I minus 1 comma j, this is I comma j plus 1, and this is I comma j minus 1. So these 4 are the neighbors of this ij spin. So spin ij has these 4 neighbors from this formula also as well. So here 2 into d is 2, so there will be 4 neighbors. So you can calculate for 3D it will be 6 neighbors, and so on. So you can already guess what will be the neighbors for 3D. So you can just add one k index for all of them, and there will be 2 others neighbors, which are basically ij k plus 1 and ij k minus 1. So that basically the 6 neighbors in 3D. So this is in 2D Ising model. So in 2D Ising model will show that in 2D Ising model we have this phase transition, and which Onsagor has solved in 1944. So that is basically the 2D Ising model solution, and there are several other features of this model, and that is the following. And so let me write it down one by one. So when Jij, you take the instead of taking it a constant, Jij if you take, so this is basically the exchange constant. So this is called exchange constant, and it basically it sets the energy scale. And this is clear, right? So whenever so Jij, if you increase the value of J, the magnitude will be increased. So that is the thing. And if so for the simplicity we take Jij equal to J for all Ij, they are same. And so now if J is greater than 0, then it is called basically the spins wants to align the spins. So if J is greater than 0, the spins wants to align parallel to each other, and we then say that the interaction is ferromagnetic. The interaction is ferromagnetic. Now if J is less than 0, the spin will be anti-aligned with each other. Spin will be spins then likely to be anti-parallel with each other, and this interaction is called anti-ferromagnetic. So this is anti-ferromagnetic interaction. And there is another thing which is, so if your Jij is equal to 0, so if your Jij equal to J equal to 0, so then the spins are non-interacting. So spins are non-interacting. So you might have heard in your statistical physics problems that there are several non-interacting spin, calculate the partition function, etc., etc. So this is what it means, the spins are non-interacting, and that means they are in paramagnetic state. Paramagnetic state. So now there is another possibility which is Jij, if this is random, and let's say can either be positive or negative. This is called spin glass. This is called spin glass. Right? So this is called spin glass. And now there is another thing. So if Jij is taken from a distribution, like the uniform distribution or Gaussian distribution, then it is called random field Ising model. So if the magnetic field, basically the magnetic field, the Bi, basically random, so if this magnetic field becomes random, then it is called the random field Ising model. So not this Ij, so let me delete it, and so this B is taken from a distribution and this is random, and then it is called random field Ising model. So that is the thing. So this is basically the thing, and there are several other possibilities as well. So let me describe it one by one. So you can in general write the Hamiltonian as the following in general form, which is minus of sum over I comma j and Jij, which is alpha into so in terms of the three dimensional, which is Six, Sjx plus Siy, Sjy, and then also with the another term beta, which is Sjz, Sjz, right? So now there are several possibilities. So if alpha equal to beta equal to 1, then it is called Heisenberg model that I was talking at that time. Heisenberg model. Now if alpha equal to 0 and beta equal to 1, it is basically the usual Ising model, because you can see that only these two term is there, and when alpha equal to 1, beta equal to 0, then it is called XY model, right, because X and Y spins are there. So this is all basically the thing which is the about the Hamiltonian of the Ising model. And you can see, if you change a bit in the J value or in the Hamiltonian, the system totally changes, and they will show several other types of behaviors depending on that. And now I will describe what is the broken symmetry, what symmetry is broken going from paramagnetic to a ferromagnetic state, and so that I will describe in this later part.